ready to go. Start from current slide. A couple of announcements for today or this week. As far as I know now, my office hours should be good through Thursday. Okay. Today, 1:15 to 3:15, same on Thursday, and on Wednesday, 3:15 to 5:15, normal. The difference, the exception is, and it's kind of a good news, bad news situation. Do any of you have Friday classes? You do, okay. Here's the good news, bad news situation. The good news is that Friday is a holiday. We're celebrating Veterans Day one day early. It's actually on Saturday. The bad news is Jacob can't go to class on Friday. So sorry about that. Get over it, okay. So, and no, don't look for any instructors, don't look for any advisors, don't look for any administrators. The college is closed on Friday, okay?
This Saturday is Veterans Day, right?
I think so, yes.
Okay.
Yeah. But we're celebrating it on Friday.
Didn't Veterans Day used to always be celebrated on a Tuesday?
The way the state of Alabama does it, they celebrate it on the day, unless it's on a weekend, okay? So that's one of the few holidays that they do celebrate only on the day, so you could have a Wednesday off, a Tuesday off, a Thursday, and that's the state of Alabama. Not many other places, I think, are as big about it, okay? Committee, right? Okay. All right. So, Friday is a holiday. Don't come to campus. Okay? I won't be here. Okay? Now, the other thing, this is not really personal, but it is something that's very important to me. I'm assuming all of you are 18 years old or older, right? Okay. I hope that means every one of you are registered to vote, right? All right, good. And I hope every one of you knows there's a big election coming up on December 12th. Not a normal time for an election, and usually these things are very low turnout. That means your vote counts even stronger than a general election because not that many people go out. I really want everybody to vote. Now, I'm not going to tell you how to vote or even who I'm going to vote for, but I'll tell you this. It's one of the most important things I think we do as a democracy. My wife is doing the numbers on it, and in the primaries for this Senate seat that's up, the maximum vote total by any candidate was 8% of the registered voters in the state of Alabama. 8% could decide who is going to be representing us. That's not a democracy. That's a small group of people who are committed to vote, and they're deciding who gets elected, okay? Get out there and vote. Get your vote, make it count, okay? And really, you have a big key to it. Your demographic is usually one of the poorest in voting. So please don't forget to vote December 12th, okay? If you're not registered to vote yet, you've still got time. Sometime later this month is the deadline for registering for then. If any of you live out of town and you're from somewhere else in Alabama, and like a lot of automotive cities are like this, or even other states, then absentee ballots, you can still do that for a while, okay? So please vote. All right, that's mine. Any questions on anything we've done so far in Chapter 2, in Section 2.4 or 5? Any questions? All right. Today, we're talking about conjugate pairs, okay? Now, the main reason we're talking about it is not that I'm going to really test you on it that much, just so you'll understand where are those other roots, those other zeros for the equation, okay? We talked about that you look at the degree of an equation, and that tells you how many possible roots you could have. If it's a fourth degree equation, you could have up to 4 roots. And Chelsea came in. Whoops. There you go. All right. But sometimes you didn't have 4 roots. And the conjugate pairs actually kind of explain why you might not have all those. All right? Note that the pair of complex zeros are usually conjugates. Now, the reason I say usually, they say are conjugates. If you have real coefficients, they're always conjugates. Always. If you have complex or imaginary parts in your coefficients, no, that's not the case. But if you have real coefficients, then guess what? We're only going to deal with real coefficients. In fact, I think we only mostly deal with integral coefficients. We do occasionally have a rational coefficient. Okay, so that is what that means. The conjugates, they're in the form, if one of them's A plus BI, the other one's going to be A minus BI. If one of them's A minus BI, you know the other one's going to be A plus BI. They always show up in pairs. Okay, so this is the statement here. Let f be a polynomial function with real coefficients. Okay, no imaginary, no complex, except for real coefficients. If A plus BI is where B is not equal to 0, in other words, this does have an imaginary part to that root, or a 0 of a function, then the conjugate pair has to be a 0 as well. Has to be. And vice versa, if A minus BI, where B is not equal to 0, is a root or a 0 of the equation, A plus BI has to be as well. Be sure you see this result is true only when the polynomial function has real coefficients. And that's all we're going to deal with is real coefficients. But if you happen to ever run into one with imaginary part and a coefficient, this rule doesn't apply. For instance, the result applies to this function, f of x equals x squared plus 1. How many real solutions do you have there? None. So how many complex do you have? 2, plus or minus I. Okay? Complex conjugates. However, if this was your function, g of x is equal to x minus I, this coefficient, that constant, is imaginary. It's not real, so this doesn't apply. Okay? There you only have one solution, and that's x equal I. You know, the complex root. Minus I is not a solution. All right. Asada? Okay. There you are. Okay. All right. Anyone else come in since the color roll? Okay. Now, we're not going to do these, but I want you to get started on it. Find a fourth degree polynomial with real coefficients that has minus 1, that's a double root, and 3i as a 0. Fourth degree polynomial function, okay? Now, remember when we say polynomial function, that has only real coefficients. When you say polynomial, that implies real coefficients. Believe in every circumstance, okay? So if that's the case, can you tell me one more 0? So fourth degree polynomial, but you only listed 3 zeros here, and one of them is repeated, so that counts as 2. Do you have another 0? What would it be? That's a complex number. If you have real coefficients, how do your complex numbers always show up? Yes, negative 3i, exactly. Conjugate pairs. The conjugate pair for positive 3i is negative 3i, okay? So those are the zeros. Now, how would you go about finding that fourth degree? And it says a fourth degree. There's many of them, but how would you find a fourth degree polynomial with those zeros? If these are zeros, what else do you know? Automatically. About that polynomial function. If x equals negative 1 is a 0, what do you know else about that? Do what? You know something else. If x equals negative 1 is a 0. I'll turn your attention back to it's actually in an earlier section, so I can't do my slides back to it. But we've done it in this section already. Okay? There was, back in 2.3, I believe it was. Maybe 2.2. Let's find it somewhere here. Page 127, 2.2. Flip back there. Okay? You see that block just above mid-page? Real zeros of polynomial functions. When f is a polynomial function, this is, okay, and a is a real number, -1 and -1 are both real numbers, okay? The statements below are all equivalent. If x equal a, like x equal -1, is a 0, that's what it tells you it is, okay? Then what does number 2 say? Number 3, I'm sorry. Page 127, top half of the page, that block in the middle, it has real zeros of polynomial functions. If x equal a is a 0 of the polynomial function, and we know it is, x equal -1, then number 3 says?
X minus a is a factor of the polynomial.
Absolutely. So what would that tell you here?
X minus 1 is a factor.
Now x minus 1. Yes, x minus a -1, which is x plus 1, is also a factor. In fact, it's a factor twice. X plus 1 times x plus 1. And even though this was talking about real numbers, what does that tell you about 3i? If that's a 0, guess what the factor is? X minus 3i. And you just told me, I think Hannah told me, that -3i was also 0. So what did that tell you? X plus 3i is a factor. There you have your 4 factors for this polynomial function. All you have to do is multiply them together. And I would start with the x plus 3i and x minus 3i over here. When you multiply those together, those are complex conjugates, right? And you know how to multiply those. The first one squared plus the second real part squared. That'd be x squared plus 9. Okay? So that's one factor. And then x plus 1 times x plus 1, you can multiply those together. You can do them in any order you want to. Multiply all those together, there's your 4th degree polynomial. So you have 4 factors, x times x times x times x, x to the 4th. Then you have some cubed terms, you have some square terms, you have some linear terms, and you'll have some constants. But those will be, that's how you get it. Now, I didn't want to take the time to do it because we're not going to mess that much with the complex part. Okay? So, watch how they do it though. Because 3i is a 0, and the polynomial stated to have real coefficients, okay? We know that the conjugate, -3i, must also be a 0, so here are your 4 zeros, just like we said. And if those are your 4 zeros, you know also what? Your 4 factors of the polynomial, which would be x plus 1 times x plus 1 times x minus 3i times x plus 3i. Okay? Now, they threw an a in here too. A is any constant. That's why I said there's an infinite number of solutions. They just said find a 4th degree polynomial. Once you find that one, you can multiply it by any number you want to. Every term in that, and you'll still have something that has those zeros. So the next thing they're going to do is probably turn around and say, well, let's let a equal 1. Okay, that'll be fine. For simplicity, let a equal 1. Okay? And then after you finish the problem, you can multiply the whole thing by any number you want to. rational, irrational, I wouldn't multiply it by a complex number, the imaginary part. Okay, so to multiply those factors together, they did the real coefficients first. That's x plus 1 times x plus 1, which is perfect square trinomial, x squared plus 2x plus 1. Multiply the complex conjugates together. That's even easier because it's the first one squared plus the next one squared. Why plus? Because minus times minus is, minus times plus is negative, but I squared is negative 1. So that makes it a plus sign. Okay? And then you take these two and multiply those two together. X squared plus 2x plus 1 times x squared plus 9. You all know how to do this, right? Okay, I don't mind doing this part of it. How do you multiply those together? Let me ask you a question before you answer that. How do you multiply 121 by 19? How do you do that? One digit at a time. Exactly. 9 times 1 is 9, 9 times 2 is 18, carry 1, that would be a 10, that would be a 1, a 2, a 1, and then you add them up. 2, 2, 9, 9. Okay? Review of multiplication, right? Well, how do you multiply polynomials together? One term at a time. Very good. Okay? So we'll erase that. And where do you want to start? On the left, on the right? Sit down. Okay, x squared times x squared is x to the 4th. Okay, then x squared times plus 9x squared. Then x, you already done the x squared times both of those. Now let's do the 2x on both of those. 2x cubed plus 18x. Okay, now let's do the constant by them. X squared plus 9. Okay? I wrote those funny, didn't I? But I did it so I can add them together. That's what you did before, right? X to the 4th plus 2x cubed. What? Plus 10x squared plus 18x plus 9. You don't have to write them strung out like that. You can write them all in a row, but then catch all your like terms and put them together. I do it like this because I tend to skip terms and miss terms, and this way it sort of helps me guarantee I may not miss them as bad. Okay? There you go. Then multiply any constant by that you want to. Negative pi halves. 14e divided by 3. Anything you want to multiply, as long as you multiply every term by it, that will be a 4th degree polynomial that satisfies those conditions. Okay? So let me erase my scratch. They don't show you how they multiply. They just say, here's the product. Okay? I think we got it right, didn't we? Isn't that what we got? Good deal. Okay, that was example 6. Okay? Let's look, they aren't going to do example 7, so let's look at it. Find a cubic polynomial function f with real coefficients that has 2 and 1 minus I as zeros. Okay. Find a cubic polynomial. So what does that mean? What degree? 3. Okay. Cubic polynomial f with real coefficients. How? What does that mean? If you know the polynomial has real coefficients, what does that mean? If you have a complex solution, a root, 0, it's going to have a conjugate. Okay? If you have real zeros of the polynomial, if you have something with an I in it, you have something else with an I in it. It's conjugate pair. Okay? So we know that it has 2 and 1 minus I as zeros. Let's see, yeah. These are your zeros. Okay? Now they have another thing. F of 1 is equal to 3. Okay. Now, how would you approach that problem? I'm not going to give you one like this, but you may have one that would have, the zeros given, and you didn't have a complex part. You still might have to find out the complex cubic polynomial with it. Okay? So how would you proceed? First thing you know is what? The cubic polynomial, how many zeros is it going to have? 3. You only listed 2. Can you come up with the third one? What? Again? It would be 1 plus I. The conjugate pair, you always change the sign of the imaginary part. 1 plus I is going to be your other 0. Cubic polynomial, 3 zeros, that's all she wrote. Okay? So what would you do then? Multiply those two together, and you know what that's going to be, don't you? Oh, wait. Okay, sorry. These are your zeros. Then what do you do? Make them into, factors. And what would this factor be? X minus 2. What would that factor be? Okay, x minus 1 plus I. And then the other one would be minus I. Perfect. Okay? Everything? Yeah. All right. Anyone else come in and says a call roll? Okay? So, now that you've got the factors, x minus 2, x minus 1 plus I, and x minus 1 minus I, what do you do with those? Multiply them together. Okay? I would do these first. That's a little messy, but you can still do it. Okay? And since it's a conjugate pair, that should give you real values. Okay? And then you multiply that result by x minus 2, and then multiply by a. Okay? This one you have to multiply by a, because then you have, let's see, Sean, right? Josh. No, I'm sorry, Josh, that's what I meant. Stopped at the wrong name, Josh. Okay. Now, let's do that in case you ever need to again, because it's a little messier. We said our 3 zeros are x minus 2, x minus 1 plus I, and x minus 1 minus I. Okay? What's that? I can't hear. Oh, yeah, okay. They will turn into a plus 1, but you're going to have some other things you have to deal with. So let's take it slowly, but you're absolutely right there. Okay? So this time I'll multiply these first. And just like we said before, let's do it term by term. X times x is x squared. X times a minus 1 is minus x. X times a minus I is minus xi. Okay? Then what? Minus 1 times the x is minus x. Minus 1 times the minus 1 is plus 1. And minus 1 times the minus I is plus I. Yeah, I'll put it here. Okay? Now, let's do the third term by each one of those. I didn't draw my line there. Okay? I times x is ix, or xi. Okay? And I times minus 1 is minus I. And I times negative I is plus 1. Perfect. Okay. Sean, all right. Okay. All right. Now we're going to add all those together. Okay. And the good news here is all the terms with i's in them cancel out. Okay. Add to 0. Which leaves us with x squared, you tell me, minus 2x plus 2. And that we're going to multiply by x minus 2. And you'll have a cubic polynomial with real coefficients. Okay? Except you don't know what that one's going to be. So let's pick it up from there, and we're going to do the rest of it. Okay? Remember, the real answer is going to be multiplied by some constant a. So after we multiply the trinomial, the polynomials together, we're going to multiply them all by a. So I'm going to erase some of this stuff because it's in my way. Can I erase this? Y'all already got it? Okay. Okay. Now, this again, it's sort of like foiling, only not. Okay, x times x cubed, x squared is x cubed, and x times a minus 2x is negative 2x squared. X times a plus 2 is plus 2x. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 2x is plus 4x. And negative 2 times positive 2 is minus 4. Add those together and you get x cubed minus what? 4x squared continue plus 6x minus 4. Now what we have to do is multiply that by a. So that'll be ax cubed minus 4ax squared plus 6ax minus 4a. Because we can multiply that by any constant that you want to. What we're going to do now is plug in x equal 1. Okay? So this is your f of x. Now we're going to do f of 1. And what would that give us? Say again? Okay, every term. If you plug in x equal 1 here, what do you get? A. Okay. Minus what? Minus 4a plus 6a minus 4a. Okay? And what does that add to? It's minus 8a plus 7a. That adds to negative a, right? And negative a is supposed to equal 3, right? Because f of 1 is equal to 3. So guess what a is? Negative 3. So that's what your a is. So now you can go back and plug in, and it would be negative 3, negative 3 times this. And you could leave it there, or do whatever you want to with it. They left it in front, and they have exactly that answer. Or you can multiply through, and that would be negative 3a cubed plus 12, negative 3x cubed plus 12x squared minus 18x plus 12. And that's exactly what they got too. They put both answers down either way you want to do it. Now, the checkpoints here I usually don't say too much about except do them. This one I'm going to say. They start off with find the quartic polynomial. What does that mean? Fourth degree polynomial. They put it in parentheses too there, but in case you hadn't run into that word, that means fourth degree polynomial. Okay. Any questions on that? Okay, just a few techniques and tools that you might need in other circumstances. All right. Let's move on to factoring a polynomial. Haven't we been doing this from day one? Yeah. Quadratics were fairly easy if they're factorable. If they're not, you can use the quadratic formula. But we've been doing that up to now. Let's start from, not quite scratch, but build on what we've done. The linear factorization theorem shows us that you can write any nth degree polynomial as the product of n linear factors. And guess what they do? They put the a sub n out front. What was a sub n? The coefficient of that x to the nth term, right? So let's put that out front, because you see, if you multiply these together, x times x times x times x, and do it n times, you're going to have x to the n. A sub n will be your coefficient. And then after that, everything gets a little wacko, because all the rest of them have some c's, multiply them in a sub n, so they come up with all sorts of other coefficients. We're not going to do any of them, we're just going to show you how it's done, okay? However, that result includes the possibility of some of the values that c sub I are complex, okay? Now, if they are complex, if some of these roots are complex, and they say nth degree polynomial, we're going to assume the polynomial has what kind of coefficients? Real. And if it does have reals, if one of these is complex, how many others have to be complex? At least one more. Why? All your complex roots are in conjugate pairs. Exactly. So if any one of them is complex, there is another one out there that has to be complex as well. Okay? And if you have two that are complex and they're not conjugate pairs of each other, then both of them have a conjugate pair. Okay. So, the following theorem says that even if you do not want to get involved with the complex factors, you can still write f of x as a product of the linear and or quadratic factors, because every one of those complex pairs are going to, when you multiply them together, you lose your i's, remember? Oh, goodness, you're blind. No, I'm sorry. You lose the imaginary parts, okay? And, okay, someone was listening. Okay, all right. So if you do that, then you have a quadratic. So your linear factors will be all those that have real c's, and then those that have complex c's. They always show up in conjugate pairs. So when you multiply them, those will be quadratic factors. All those real ones are going to be linear factors. Okay. So the factors of a polynomial. Every polynomial of degree n greater than 0, that includes just n minus 7. You know, that of the x minus 7, degree 1, that would be fine too. Okay? With real coefficients, that's required, can be written as the product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. Okay? Because if they had real zeros, you could write them as linear factors, not quadratic factors. So the conjugate pairs will show up as quadratic factors. When you multiply them together, all the others will be linear factors. All right. So you know you can do it. The question is how to do that. Okay. So a quadratic factor that has no real zeros is said to be prime or irreducible over the reals. Okay, I think you've run into that probably somewhere before. A quadratic factor with no real zeros, x squared plus 1. There aren't any real zeros for that. Okay, so anything that does no real zeros, we say it's irreducible over the reals. Note that this is not the same as being irreducible over rationals. Okay, I don't know if you've run into that before, but that would be if you can't factor a quadratic, and then you use a quadratic formula and you get irrational solutions, then that would be not irreducible over the rationals. Okay, but if you can't even get it with those, then that would be irreducible over reals. That means your roots are going to be complex, and they're always going to show up in conjugate pairs. like this one is going to be x minus I times x plus 2. It's irreducible over the reals because you can't factor that with real numbers. And therefore, it's also irreducible over the rationals as well. On the other hand, the quadratic x squared minus 2 is factorable, not with integers, but with irrational numbers. X plus the square root of 2 times x minus the square root of 2. Because 2 is the square root of 2 squared, right? And then that's the difference of 2 perfect squares. It's just they're not rational numbers. They're irrational. That's irreducible over the rational, but reducible over reals. Those are real numbers, okay? These are not real numbers. Those are complex imaginary numbers. Okay. Most of this is nomenclature. So let's do, it says find all the reals, all the zeros of f of x equal x fourth minus 3x cubed plus 6x squared plus 2x minus 60, given that x plus, 1 plus 3i is a zero of that function f. Okay? Now, again, you're not going to have one like this. I'm going to try to avoid these on the test. But it's still not a bad practice to know how to do this. If this is a zero, and they told you it is, what else do you know? Do you know at least one more zero? Yes, 1 minus 3i. So if those are two zeros, what would be their factors? So you know that 1 minus 3i is also a zero. So what would be their factors? The factor for this one would be x. Help me. For the top. What would be its, if x is equal to, that's an ugly x, and that's even worse. Goodness gracious, they're getting worse. Okay, let's start over here. Okay, x equal 1 plus 3i. What would be the factor corresponding to this? X minus 1, say again, minus 3i. That would be a factor. What would be the factor corresponding to this one? Not that hard. It would be x, what do you say? Negative 1 plus 3i. Very good. There's the other factor. And if those two are factors, what can you do? Multiply them together. What does that give you? X squared minus x third one? No, plus 3xi. Okay? Let's do the second number. Minus x. Say again. Plus 1. Minus 3i. Okay? And let's do the last one. Negative 3xi plus 3i. Second, minus 9i squared, which would be, what's I squared? Negative 1 times negative 9 is? Plus 9. Very good. Okay? Now, combine these, and what do you get? X squared minus 2x plus 10. They go away. Very good. So here we know a factor, a quadratic factor of that function. So can I erase everything but the quadratic factor? Is that okay? All right, so let me erase that. Okay. Don't let me get carried away and erase what I need. Okay. All right, what are we going to do now that we know that's the factor of that polynomial? Or at least they told us it was. And we believe them, don't we? What do we do with it? If this times something is equal to that, what can we do? To find out what the that is. Divide. And I don't think we can use synthetic division, can we? Because this has a coefficient of 1, but an exponent not 1. So you can't do that. So guess what we got to do? Yay, team! What is it? Long division. So on the outside goes x squared minus 2x plus 10. And on the inside of the house goes x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. Now what did you better do? Check that you have every term covered. Look at your powers. 2, 0, 1. 4, 3, 2, 1, 0. I said that back. 2, 1, 0. 4, 3, 2, 1, 0. Yes, you got every term factor. You don't need to put any extra zeros in there. Got it. So now we can go to town. First step. X squared will go to x to the fourth. How many times? X squared times. Then what do we do? Multiply. X squared times x squared is x to the fourth. X squared times minus 2x is negative 2x cubed. And x squared times 10 is plus 10x squared. And then what do we do? Change signs and add. Or subtract if you prefer, but I like changing signs and adding. So that's going to make this. Oh, I hit the wrong one. Okay, sorry. That's a plus there and a minus there. Okay. And that you get when you add these? 0, negative x cubed, negative 4x squared. And then what do? Bring down the plus 2x. Okay? Now what? How many times will x squared go into negative x cubed? Negative x times. Very good. Then you do what? Multiply. Negative x times x squared is negative x cubed. Negative x times negative 2x is second plus 2x squared and squared. Okay. Negative x times 10 is negative 10x. And then what do we do? I'm going to have to erase my thing. I've already copied it up here, so I don't need that anymore. Or that ugly thing. Okay. Now you what? Change signs and add. So those become plus, and this other one becomes a minus. Okay? Those add to 0. This goes negative 6x squared plus 12x what? Negative 60. Very good. Now we divide. Okay, x squared going to negative 6x squared how many times? I couldn't hear. Negative 6 times. Because negative 6 times x squared is negative 6x squared. And negative 6 times negative 2x is positive 12x. And negative 6 times positive 10 is? Negative 60. I don't think you have to change signs to add here. You can see those are identical. So when you subtract them, they go to 0. When you change signs to add, they go to 0. You've done it. But that still doesn't give you the other zeros, does it? How do you get your other zeros?
You find the zeros
Of this one, yeah. Set that equal to 0, and how would you find the zeros of that? Say again? Factor! Very good. Okay? If it's factorable, we factor it. And if that's factorable, what would be your first factor? X times x. Then we look where? Sign of the last term is negative. So what does that give up? 1's plus and 1 minus, okay? And then you want two numbers who multiply to be 6, but whose difference, because they have different signs, is 1. 3 and 2. And which one wins what? Which sign goes with which? A little louder. 2 on the first one and 3 on the next one, because the minus in the middle wins, so you got to pick the bigger number with that one. I think we've done it. Let's check and see. X times x is x squared. Minus 3x plus 2x is minus x. Minus 6. Yes, that worked. So your other two zeros are x equals negative 2 and x equals 3. See, y'all are real good about going from factors to zeros, but I have to pull teeth to get you going from 0 to factors. It's just the other way. You're doing the same thing, right? I don't like pulling teeth. Okay, no. Okay. I'm not a dentist. Okay. So there's your zeros. They gave you 1 plus 3i. You gave me the second one, which was 1 minus 3i, and then we found the other two, x equals negative 2 and x equals 3. Good. So you see how to do that. Let's see how they did it. Let me, all right. Remind me? Huh? Sandria. Okay. All right. Good deal. All right. Let me erase all the ink here. We're doing example 7 on page 156 in chapter 2, section 2.5. Okay? Because the complex zero occurs in conjugate pairs, knowing that the polynomial function has all real coefficients, then you know that x minus 3i, 1 minus 3i is also a 0. And if those are zeros, then x minus 1 plus 3i and x minus 1 minus 3i are both factors of that. Now, we didn't say that. Y'all did it directly by multiplying, distributing the minus signs across the things. That gave us, goodness gracious. Now, this is another way to do it if you don't like doing each term, okay? What they did was take off the parentheses here and put it there, and that made this a minus 3i. You've got to remember to do this. That's why I don't do it this way. And do the x minus 1 here and do the x plus 3i there. Now you have the sum times the difference of two entities, and that's going to be the difference of two perfect squares. So if you get this step right, which is real easy to forget a sign there, but if you get it right, then that makes it maybe a little bit easier to do. You get x minus 1 squared minus 3i in parentheses squared, okay? That's how they're going to do it. If you like that better than doing term by term by term, do it this way. If you don't like this way, do it term by term by term. That'd be x minus 1 squared minus 9i squared. Now, I don't like, okay. They multiplied the 3's and they didn't multiply, they just wrote it as I squared, which would be x minus, goodness gracious, did they ever skip steps here? This would be x squared minus 2x plus 1, and this would be plus 9, so that's x squared minus 2x plus 10. All right, they skipped a lot of steps doing it this way too. If you like that way, go for it. But if you don't mind doing the term by term, to me, that's a little less likely to make a mistake. But that's up to you, okay? So here we have one factor of that quartic polynomial. So what we can do is divide that into the quartic polynomial. And they like to put their divisor, their quotient down there. I like it over here. But that's exactly what we did. I didn't write 0 under it, but we knew that was a 0. And then once you got your quotient, x squared minus x minus 6, exactly what we got, then you factor that. Well, no, you write it as a factor of it, and then you can write this one. Leave this as a quadratic, because that's irreducible in the reals, okay? But this is not irreducible in the reals, so you factor that. X minus 3 times x plus 2. Now you can conclude your zeros. We already were given that one, okay? We knew this one was going to be 1, and now we've got 2 more, x equal 3 and x equal -2. Got it? See how it works? Any questions? Blah, 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 huh? Okay. Any questions? Okay. Now, in example 7, without being told that x plus 3i is a 0, you can still find all the zeros by using synthetic division to find the reals -2 and 3. What would you use for your synthetic division? Remember way back? Rational zeros test. Go back to your rational zeros test. After a while, you would find the x equal 2, and then you x equal -2, then you would find the x equal 3, and then you get an irreducible form, and that would give you your last 2. Okay? That's how we do it. Now, actually, yeah. So you could do it without being told you do have a complex 0. Okay? And that's how we're going to do the rest of them. That was example 8 we just did. They are skipping example 9. So let's do example 9. Let's back up. Okay, let's do example 9 here. Now, how in the world okay, we did example 7. They didn't even have example 7. Okay. Their example 7 was our example 8. Okay, so that's how the examples got off numbered here. Okay. Find the zeros of this polynomial function. F of x is equal to x to the 5th plus x cubed plus 2x squared minus 12x plus 8. Now, when I was writing that, did y'all hear any bells go off, alarms, warnings? You didn't? You're missing an x to the 4th. Good catch, okay? So when we come to do something with it, you got to remember to put that term in, okay? That's what you need to do. Start thinking and recognizing these things as soon as they pop up. Okay, got to remember that. Okay. Now, where would we be? What it says to do here is find the zeros. Well, actually, the example says that. The problem says write this thing as a product of linear and list all of linear factors and list all the zeros of the function. Okay? So we're going to do two things. Write it as linear factors and listing all the zeros of the function. Okay? So, where would we begin? I gave you a hint just a few minutes ago. What test will we use first? Rational zeros test. Very good. How does that go? All the rational zeros of that polynomial function will be of the form P over Q, where P is what? Oh, it was a long time ago, wasn't it? All the possible factors of your constant, which is 8. What are possible factors of 8? All of them. Plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Very good. Over your denominator, and what's its factors? All the possible factors of the leading coefficient. What's the leading coefficient? 1. That's going to be easy, plus or minus 1. So we don't need any denominators. 1 in the denominator is not going to give us anything. So all your possible zeros are those 8 in the numerator. Okay? Which one you want to start with? 1. Okay, that's going to be easy. How do we determine if 1's a factor? Or 0? You just write down the coefficients. Yeah, you just plug in 1. F of 1 would be 1 plus 1 plus 2 minus 12 plus 8. See what it adds to. Those are ugly numbers, aren't they? Okay, let's add our positive. 8 and 2 is 10, 11, 12. Hey, ding, ding, ding. We have a 0. Okay? X equal 1 is a 0. They said find all the zeros. We found one. X equal 1. Okay. Guess what we're going to have to do, though? Go back and do synthetic division anyway. But we already know it's going to work. Okay? So what do we put on the outside? 1. What do we put on the inside? 1. 0. Very good. 1, 2, negative 12, 8. Do we have enough numbers there? How many numbers we got? 1, 2, 3, 4, 5, 6. What's our exponent? 5. Yes, one more than that. We got enough. Then what do we do? Skip a line, draw a line. Okay, then we do what? Bring down the 1. And then you multiply, and that gives us. Then you, and that gives you. And then you, and that gives you. Boy, y'all are stuck in the rut, aren't you? Okay. 2, 2, 4, 4, negative 8. Negative 8. Don't be surprised. You knew that was going to turn out being a 0 because that was a 0. Okay? What do we do next? Say again? No. You try 1 again. It may be a double root. So keep trying until 1 won't work, and then you move to another one. So do 1 again. And again, you skip a line, draw a line, and bring down the 1. 1, 2, 2, 4, 4, 8, 8, 0, ding, ding, ding. See, if we hadn't done that second one, we wouldn't have realized it was a double root. Okay? Now, I'm going to cheat a little bit here. Okay? I'm going to tell you something we're going to hit a little bit later. Not long, very soon. Probably not today, though. Notice here, you had at least one change of sign here. If all these have been positive, you know that no positive number is going to go into it because they're going to keep adding. You had a negative, it worked. Here you have at least one negative sign. So try another positive. Here you have all positives. So guess what? Don't try plus 2, don't try plus 4, don't try plus 8. They're just going to make bigger and bigger and bigger numbers. There's no way to get it to subtract. So let's move to our negative numbers. Okay? What negative number might you choose? How about negative 1? Okay, again, we skip a line, draw a line, bring down 1. What does this give us? Negative 1, 1, negative 1, 3. Ain't gonna work, is it? Okay, so forget negative 1. Okay, so let's erase negative 1. Ooh, I erased part of my 4 too, also. Okay. Now, what's the next one? Negative 2. All right. What would that give us? Negative 2, 0, 0, 4, negative 8, 0. Ding, ding, ding. We found another one. So x equal 1, x equal 1, and x equal negative 2. What's that? Because, and we haven't gotten there yet. I just cheated, okay? And what I said was when you get all positives down here, you know that no more positives will go in here because then the numbers will keep getting bigger, bigger, bigger because you have nothing to subtract them off. We'll hit that next class, okay? So right now, that's why we stopped doing the positives and went to the negatives. Negative 1 didn't work, negative 2 did. What does this leave you with? Do you do synthetic division again? No, because I don't have any room. No, that's not the reason. Why don't we do it? That's a quadratic. And what quadratic is that? Say again? X squared plus 4. Okay. There's our other factor. Okay. Now I can tell you right now, this is going to have what kind of roots? Okay. It will be. No, actually it's not. It's a complex root. An imaginary part. Because there's no way x squared plus 4 is ever going to be 0 in the real number system, right? Can't happen. You square any real number and it's positive, add 4 to it, it's more positive. So you never will get 0 from that. So this will give you complex answers with imaginary parts. So guess what? We're not even going to, you know what they are. They're conjugates of each other. What are they?
X minus 2, x plus.
No. That would be x squared minus 4. This is plus 4. These are complex. They have imaginary parts.
X minus 2 times 4i.
Yeah.
And then x
Negative 2i and plus 2i. Exactly. Complex conjugates of each other. That would work. That's what they're looking for. We can write them down there. Those are the real zeros. I'm going to stop there and say real zeros. Can you give me the factorization of this? Now, they won't all be linear factors. This is a factor. What are 2 other factors? 3 others. Come on, hurry, hurry. Yeah, you know it. You go real easily one way, you don't do it. Okay, this would be, I'm pulling teeth again, right? X minus 1 times another x minus 1, that'd be x minus 1 squared. And the other one would be x, what? Plus 2. Okay. All right. Those are your factors. Sorry we run. Why were y'all packing up? Y'all still got 4 minutes, okay? Goodness gracious, you had me rushing here, thinking it was time to go. It wasn't. So those are your factors are here. 3 linear factors, 1 quadratic factor. Your real zeros are 1, 1, and negative 2. Double zero at 1, single 0 at negative 2. These others would be complex zeros. I'm not going to have you do the complex zeros, but you've done the factorization with linear and quadratic factors, and you found your real zeros. That's all you'll be required to do because we're not going to deal that much with the complex part. Okay, there is a checkpoint there. Well worth doing the checkpoint as soon as you can. Now, here are some other tests that help you find the zeros of the polynomial. I actually cheated and gave you one, but we haven't gotten there yet. Here's something else. You know that an nth degree polynomial function can have at most how many real zeros? An nth degree polynomial function, how many, most number of zeros you can have? N, okay? Whatever the degree is, you can't have up to that many real zeros. Or sometimes you don't, okay? sometimes you have some complex zeros. What do the complex zeros always show up in? Pairs. Conjugate pairs, exactly. Of course, many nth degree polynomials do not have that many real zeros, but all your complex zeros will going to show up in conjugate pairs. So, for instance, if this is, how many real zeros does that have? None! Because there's no real zeros that when you square it and add 1 to it, it's going to be a 0. Can't happen, not in the real number system. So both of its zeros are going to be complex, okay, with imaginary parts. Has no real zeros. How about this one? It could have up to how many? 3, but really we know it only has 1. How do we know that? Because we know that x cubed graphs like this, and x cubed plus 1 just goes up 1. So it only crosses the x-axis 1 time. Can anyone tell me what that real zero is? X equals?
1.
Negative 1. Because positive 1 would be 2, negative 1 would be negative 1 plus 1 is 0. Yes, that's your one real zero. So guess what the other two are? Complex. Okay? With i's in them. That has only one real zero. Hint. Any odd degree polynomial function, what's its end behavior going to be?
Negative infinity.
Exactly. So guess what? Polynomial function is always smooth and continuous. Got to cross 0 somewhere. All odd degree polynomials got to have at least one real zero. Got to. No way around it. Even could have 1 or 2, maybe not, but odds have to have at least 1. They may have more than 1, but they got to have at least 1. So they start low and go high. These are up and up or down and down. They may never cross the x-axis. Okay? Oh, boo hiss. We've run out of time. Okay. We will start next time with Descartes' rule of signs. Okay? All right, let me give you a few homework exercises. I know that you don't want to leave without those. Okay. Do any of the odds any of the odds 9 through 13. 9 is in calcview.com, the others are in calccheck.com. Do either 15 or 17 or both. Do any of the odds 19 to 27. 25 is calcview. Do either 29 or 31. 29 is calcview. Do either 33 or 35 or both. 37 or 39 or both. Any of the odds 41 to 45. 43, well, you don't have to do those because they have imaginary parts in them. You don't have to do 49 to 47 or 49. Those have imaginary parts. You can if you want to. Try doing 51 or 53, okay? And try doing any of the odds 55 through 59. 55 is on CalcView. Try doing any of the odds 61 to 71. 69 is on CalcView. And try doing any of the odds 73 to 77. Okay, stop there. Up to 77. All right, I think I feel some quizzes coming on. Okay. Yeah, I'm out. Okay, take care, Will. I think it's out of stock. Yeah, it's fine. That's good. I'll try to keep them together. Thank you. Okay, good deal. Y'all just waiting to see me or not? Oh, it's out of stock.
Okay. Hey.
All right, good deal. Thank you. Okay. Well, it can't be over 25. It can be be over x minus x plus 2.
And that'll be my final answer.
Okay.
Right.
Okay. Now, you see, you got a minus 25x here. You brought down to plus 6.
Right.
What you didn't do is do this into that. That would be a minus 25. Then you multiply again.
And then do the
Yeah.
6.
Well, no, I mean, every time you see, you do this into that because that'll go. You do this into that because that'll go. You do this into that because that will go. Minus 25 times. So that's the minus 25. Then you multiply. Then when you get a remainder, it will probably have just a number.
Right.
And then you put that number over x minus 2, not over 25.
Okay.
X plus 2.
I understand.
Yeah. Okay.
Okay, so I probably did this one wrong too. So can I give this to you Thursday?
That's perfect.
Because I'm almost done.
Yeah.
It's just little stuff like that.
Yeah. I'd rather grade a good paper than
That's
one that has
true,
errors in it. Okay.
Okay.
It's much easier for me to grade. I want you to do the work, not make me do the work, okay?
Of course.
Of course, okay. You gotta get your priorities right here,
Yeah,
okay?
I know.
Okay. Working on yours still too?
I am.
Good deal. All right. I think I'm catching up on grading. Here comes another pile, but glad to do it. Okay, Eric, getting show today. I need to end this. Yes.
My goal is